Hello students, we require energy for doing our work and also for our bodily activities. So, let us see what are the energy requirements for humans. What is the definition of energy requirement? Energy requirement is the amount of food, energy needed to balance energy expenditure in order to maintain body size, body composition and the level of necessary and desirable physical activity consistent with long term good health. This includes the energy needed for optimal growth and development of children, for the deposition of tissues during pregnancy and for the secretion of milk during lactation, consistent with the good health of mother and child. Daily energy requirements and daily energy intakes. Recommended energy intake is the amount of energy that should be ingested as a daily average over a certain period of time. Heart rate monitoring, a method to measure the daily energy expenditure of free living individuals based on the relationship of heart rate and oxygen consumption and on minute by minute monitoring of heart rate. Total energy expenditure, the energy spent on average in a 24-hour period by an individual or a group of individuals. By definition, it reflects the average amount of energy spent in a typical day, but it is not the exact amount of energy spent each and every day. Physical activity level is the total energy expenditure for 24 hours expressed as a multiple of BMR and calculated as total energy expenditure or BMR for 24 hours. In adult women and non-pregnant, non-lactating women and adult men, BMR times and physical activity level is equal to total energy expenditure or the daily energy requirement. Now, the components of energy requirements are the human beings need energy for the following. One is basal metabolism, that comprises a series of functions that are essential for life, such as cell replacement, synthesis, secretion and metabolism of enzymes and hormones, to maintain body temperature, uninterrupted work of cardiac and respiratory muscles and brain function. The amount of energy used for basal metabolism in a period of time is called basal metabolic rate and is measured under standard conditions that include being awake in the supine position after 10 to 12 hours of fasting and 8 hours of physical rest, and being in a state of mental relaxation in an ambient environmental temperature that does not elicit heat generating or heat dissipating processes. Depending upon the age and lifestyle, BMR represents 45 to 70% of total energy expenditure and is determined mainly by the individual's age, gender, body size and body composition. Metabolic response to food. Eating requires energy for the ingestion and digestion of food and for absorption, transport, interconversion, oxidation and deposition of nutrients. These metabolic processes increase heat production and oxygen consumption and are known by the terms such as dietary induced thermogenesis, specific dynamic action of food and thermic effect of feeding. The metabolic response to food increases total energy expenditure by about 10% of the BMR over a 24-hour period in individuals eating a mixed meal. Physical activity, this is the most variable and after BMR the second largest component of daily energy expenditure. Human performs obligatory and discretionary physical activities. Growth, the energy cost of growth has two components: the energy needed to synthesize growing tissues and the energy needed for deposition in those tissues. Pregnancy. During pregnancy, extra energy is needed for the growth of fetus, placenta and various maternal tissues such as uterus, breasts and fat stores, as well as for changes in maternal metabolism and increase in maternal effort at rest and during physical activity. Lactation. The energy cost of lactation has two components, and one is the energy content of milk secreted and second, energy required to produce that milk. Direct and indirect calorimetry. The amount of energy released from foods and the amount of energy expended by an individual can be obtained by direct and indirect calorimetry. The chemical changes that occur when carbohydrate and fat oxidize during respiration in the body are identical overall to the chemical changes when these chemicals are burnt in air. This is the principle of direct calorimetry. The amount of energy released or expanded is measured by the heat produced. Indirect calorimetry is based on the principle that when an organic substance is completely combusted, either in calorimeter or in human body, oxygen is consumed in amounts directly related to the energy liberated as heat. So, the direct calorimeter is done by the bomb calorimeter, where the energy value of food is estimated, and direct calorimetry is also done by Atwater Rose respiration calorimeter, where the energy expenditure during BMR and resting energy expenditure of at light activity is measured. Whereas indirect calorimetry is measured by Benedict's oxycalorimeter, where the energy value of food is determined and also the determination of BMR is done. The other equipment for measuring indirect calorimetry is Benedict Roth respiration, where a Douglas bag is used and energy expenditure during work is calculated by Max Planck respirometer and Cofrani-Michaelis respirometer. Total energy requirement. The total energy requirement of an individual is the level of energy intake from food that will balance energy expenditure. Estimates of energy requirements could be based on the measurements of either energy intake or energy expenditure. In practice, measurement of energy expenditure intake are usually less reliable than measurement of physical activity, consistent with long term good health and that will allow for maintenance of economically necessary and socially desirable activity. In children, pregnant and lactating women, the energy requirement includes the energy needs associated with the deposition of tissues or secretion of milk at rates consistent with good health. The human body's total energy needs can be subdivided into three separate categories. The energy required to maintain basal metabolism, the basic essential metabolic processes required to keep the body alive and healthy, where applicable growing at an appropriate rate. The energy required to power physical activity, meaning all the muscle movements, and the energy that is released as a result of thermic effect of food. It is the process of increased energy expenditure, and therefore, heat release is inevitably occurs between 1 to 3 hours after a meal due to the stimulating effect that the nutrients of food have on metabolism in general. So, the components of energy expenditure are thermic effect of food, which is about 10 to 15% of total energy expenditure, basal metabolic rate, which is 55 to 60%, and physical activity, which is 20 to 30%. Generally, basal metabolism represents a person's largest expenditure of energy followed by exercise and the thermic effect of foods. Of these categories, energy spent in physical activity is most responsive to voluntary control. Basal metabolic rate, the amount of energy required to carry on voluntary work of the body, is known as basal metabolic rate. It includes functional activities of various organs such as brain, heart, liver, kidney and lungs, all vital organs. The secretory activities of glands, peristaltic movement of gastrointestinal tract, oxidation occurring in resting tissue, maintenance of muscle tone and body temperature. The brain and nervous tissues account for 1/8 of the energy utilized at basal state, and lungs, liver, heart and kidney for the additional 3/5. Measurement of basal metabolism, direct calorimetry and indirect calorimetry. One disadvantage of direct calorimetry is that the measurements can only be made over periods of several hours or more, since the technique assumes that there is no net increase or decrease in body temperature over the measurement period. And indirect calorimetry is based on the fact that oxygen is used and carbon dioxide produced is in proportion with the heat generated. So, BMR is measured by indirect calorimetry under the following conditions. The individual should be in post absorptive stage, that is 12 to 16 hours after the meal, then reclining but awake, reset before the test is necessary if there has been any activity in the morning. It is done best as soon as the individual gets up without getting out of the bed. Relaxed and free from emotional upsets or fear to test itself. Normal body temperature and comfortable room temperature and humidity of 21 to 24 degrees centigrade. Then respiratory quotient is defined as the ratio of the volume of these carbon dioxide produced to the volume of oxygen used on oxidation of a given amount of nutrient. So, the formula is RQ is equal to carbon dioxide exhaled divided by oxygen consumed. So, the respiratory quotient varies of the food that is being oxidized. For example, for pure glucose, the respiratory quotient is 1, that is the carbon dioxide exhaled is equal to the oxygen that is consumed, whereas for fatty acid the respiratory quotient is 0.7, and for the protein the respiratory ratio is 0.82. The respiratory quotient as post absorptive stage when basal metabolism is determined is 0.82 for protein, and the body derives energy from oxidation of carbohydrates at the rate of 50%, fat 40% and protein 10% present in the body. The respiratory quotient for alcohol is 0.66. Over 24 hours, the respiratory quotient should reflect the diet composition if the individual is in energy balance. The RQ is useful guide for the mixture of nutrients being oxidized, and if the protein oxidation can be determined from urinary nitrogen, the amount of fat and carbohydrate oxidized can be calculated. It is known that 1 gram of urinary nitrogen arises from the metabolism of 6.25 of protein. Some of the important findings from the studies of RQ are: immediately after the meal, almost all the food metabolized is carbohydrates. So, the RQ at the time approaches 1, and approximately 8 to 10 hours after the meal, the body has already used up most of it readily available carbohydrate, and the respiratory quotient approaches that of fat metabolism, which is approximately 0.7. In diabetes mellitus, very little carbohydrate can be utilized by the body cells, under any conditions because insulin is required for this. Therefore, when diabetes is very severe, the RQ remains most of the time very near to that of fat, that is 0.7. This is another test for diabetes. Basal metabolism is usually determined using the apparatus Benedict and Roth, where the subject wears a nose clip and breathes to a mouthpiece which is connected to the apparatus by two tubes. The subject breathes in oxygen through the respiratory valve and breathes out into the carbon dioxide absorber and then through the respiratory valve into the spirometer bell. The amount of oxygen used is recorded on the revolving drum by the pen attached. Since the subject is in post absorptive stage, RQ is assumed to be 0.82 and the calorific value of 1 liter of oxygen consumed is taken as 4.8 kilocalories. For example, if the oxygen consumed in 6 meters is 1100 ml, heat produced in 6 minutes is 4.8 into 11 liters. That is 1 gram of protein is equal to 5.28 kilocalories. And heat produced in 24 hours is equal to 5.2 by 6 into 60 into 24. That is for whole day it comes to 1247 kilocalories. Therefore, the basal metabolism of individual for 24 hours is 1247 kilocalories, which is about 50 to 60% of the whole day's total energy expenditure. Closed circuit or indirect calorimetry. This is a closed circuit system in which the subject receives oxygen only from a measured source of oxygen rich air and exhales into the container in which the carbon dioxide and water are removed, while the remaining oxygen and nitrogen are recirculated. The amount of oxygen in the air mixture is measured before and after each standard 6-minute test, allowing the amount of oxygen consumed to be determined. The use of 1 liter of oxygen under normal conditions of temperature and pressure corresponds to the release of 4.82 kilocalories of energy when RQ is 0.82 under basal conditions. Thus, the kilocalories released during the consumption of any volume of oxygen can be readily calculated under these conditions. Open circuit indirect calorimetry. In this method, the normal room air is breathed in and the exhaled carbon dioxide generated from it is collected and measured. Knowing the amount of carbon dioxide produced in a given time allows the calculation of the amount of oxygen consumed to generate that carbon dioxide, and thus the amount of energy released can be calculated. The open circuit indirect method is even less expensive than either direct calorimetry or closed circuit indirect calorimetry. It also reduces the possibility of errors as a result of stimulation of metabolism caused by the use of oxygen rich air in a closed circuit method. Determination of basal metabolic rate by calculations. Basal metabolic rate can be calculated not only by direct and indirect calorimetry, but also by using the formulae taking body weight into consideration. So, for females, weight in kg into 0.9 kilocalories into 24 hours, whereas for males, weight in kgs into 1 kilocalorie into 24 hours. Then Harris-Benedict equation is another one for calculating the basal metabolic rate, where for female it is minus 655.5 plus 9.56 into weight plus 1.85 into height minus 4.68 into A. For males it is minus 66.5 plus 13.75 into W plus 13.75 into W plus 6.75 into A. Third is the metabolic body size, where it is 70 into weight in kgs. The fourth method is FAO WHO UNO equation, which is for females it is 8.7 into weight plus 829, and for males it is 11.6 into weight plus 879. BMR for Indians can be predicted by using the table to calculate the BMR for an individual male Indian aged 45 years using the formula BMR is equal to 10.9 into body weight in kgs plus 833, which comes to 1487. Similarly, the equations for predicting BMR from body weight in kilograms is for a male of 18 to 30 years, the BMR is calculated as 14.5 into weight plus 645, and for a male 30 to 60 years, the calculation is 10.9 into weight plus 833, and above 60 years it is 12.8 into weight plus 463. For females between 18 to 30 years, the formula is 14 into weight plus 471, whereas 30 to 60 years it is 8.3 into weight plus 788, and for females above 60 years it is 10 into weight plus 565. The comparison of energy cost of some of the common activities in terms of BMR units is, we can take the energy cost of activities in terms of BMR units. When it is sitting quietly, it is 1.2, and standing quietly 1.4, sitting at desk 1.3, standing and doing lab work, it consumes 2 BMR units, harvesting 7.4, and hand saw 1.58, typing, sitting and typing it's 1.58, walking at 3 miles per hour 3.71. Energy requirements during work. Physical activity includes both the cost and quantum of activity as well as the type of activity, namely essential, which includes economic or occupational activities, and discretionary activities including household tasks, social activities, and activities aimed at maintenance of physical fitness. Then we have another method called factorial method. Using the factorial method of FAO, WHO, UNO expert consultation has derived the BMR factors for computing daily energy requirements for both men and women engaged in sedentary, moderate or heavy activity. The BMR factors for Indian men and women are 1.6, 1.9 and 2.5 respectively for the 3 categories of activity, that is sedentary, moderate and heavy work. There is a wide variation in the energy cost of any activity both within and between individuals due to differences in body size. Now, it is common to express the energy cost of activities of BMR of Indians have 10% less BMR for the same age, height and weight for height. Physical activity accounts for 20 to 40% of total daily energy expenditure in most individuals. The energy expended in activities depends upon the type of activity and the time spent in different activities. Energy cost of activities are expressed as multiples of BMR or resting metabolic rate. Indirect calorimetry is the energy metabolism during work, which can be determined by using the various equipment like Douglas bag and Max Planck respirometer. The general principles underlying the above methods are: measuring the volume of expired air during work for fixed periods of 5 to 10 minutes, collection of sample of expired air for the analysis of oxygen and carbon dioxide content, calculation of oxygen consumption, carbon dioxide output and respiratory quotient, and calculation of energy output from the respiratory quotient and oxygen consumption. Although the Douglas bag has been used for many short measurements of energy expenditure at rest and during exercise, it is not an ideal for use during heavy exercise, as the bag may fill in few minutes and may physically interfere with the exercise. So, the Douglas bag is used for determining energy expenditure during work. The subject is wearing a 100-liter capacity bag which is partly filled with expired air. The cylindrical box attached to the mouthpiece contains valves so as to arrange that the subject breathes the atmospheric air in and breathes out through the corrugated tubing into the bag. Several probable respirometers have been designed to overcome these problems by measuring expired volume of air at the time of collection, thereby removing the need to store all the expired air. The first portable respirometer to be developed for exercise was Cofrane-Michaelis respirometer, in which only a small sample of expired air is stored for subsequent analysis in the laboratory. This has been replaced by instruments which incorporate oxygen analyzers as well as gas, volume meters and electronic components to calculate energy expenditure instantaneously. Consumed potassium weighs only 400 grams and incorporates both an oxygen sensor and a radio transmitter to relay the data into the receiver at the base remote from the subject. Whole body indirect calorimeters operate on the same principle, but provide a small ventilated room for the subject in which he or she can carry out some of the activities of a normal day. A number of indirect calorimeter chambers have been constructed with volumes ranging from 5 to 25 cubic meters. In majority of these systems, both oxygen and carbon dioxide are monitored continuously and the subjects follow a fixed routine of meals, exercise, recreation and sleep. In this way, a value for 24-hour energy expenditure with a reproducible activity pattern may be obtained. Thermic effect of food. The third category of energy requirement to be taken into account is estimating the total energy needs that is providing from the thermic effect of food. Earlier, this was known as specific dynamic action of food. The energy corresponding to the thermic effect of food includes the energy cost of absorption, metabolism and storage of nutrients within the body. In this, as a result of the stimulation of metabolism increases, the metabolism occurs from 1 to 3 hours after the meal. Processing of food in the stomach and intestine of all nutrients in the blood and body cells causes heat production. The magnitude of thermic effect of food overall is that 10% of needs for basal metabolism and activity. The ICMR has recommended dietary allowances for energy as based on the work category. For man, the sedentary worker requires 2320 kilocalories, moderate worker 2730 kilocalories and heavy worker 3490 kilocalories. Whereas for women, sedentary worker 1900 kilocalories, moderate work 2230 and heavy work 2850 kilocalories. And for a pregnant woman, it is an addition of 350 kilocalories apart from the regular amount. And for lactating women, between 0 to 6 months, an additional 600 kilocalories and 6 to 12 months, an addition of 520 kilocalories. And since the energy requirement for infants is high, 0 to 6 months it is 92 kilocalories per kg body weight per day and 6 to 12 months 80 kilocalories per kg body weight per day. For children between 1 to 3 years, it is 1060 kilocalories, 4 to 6 years 1350 kilocalories, and 7 to 9 years 1690 kilocalories. And for boys between 10 to 12 years, they require 2190 kilocalories, and 13 to 15 years 2010 kilocalories, 16 to 18 years 2750, whereas for girls 10 to 12 years they require 2330 kilocalories, 13 to 15 years 3020, and 16 to 18 years 2440 kilocalories. So, students, today we have dealt with the energy requirements for humans, which has included on the measurement of the basal metabolic rate, the respiratory quotient, thermic effect of foods, and what is the recommendations made by the ICMR on energy requirement.